Hey, this is Yash, and this is my AE 2220 Creative Assignment 2, my lecture on friction, both rolling and slipping. So to start, I'm going to give a little introduction and some pre-topic concepts. So the first question being, what is friction? Friction is the force that resists the motion of a body. And in most cases we're dealing with today, this is a cylinder for the sake of moment of inertia being the same throughout all the problems we look at. Uh, the equation of friction, aka the maximum friction, is the friction force equals the coefficient of friction mu times the normal force n. And if you can see on the diagram on the right, if for example the motion points to the right, so the velocity, and this is my right, then the friction will point to my left, and vice versa. If the motion is to my left, friction will act to my right. Now, to go over some equations for 2D motion, we learned this a couple lectures earlier. So the equations are the sum of the forces in the x direction equals the mass times the double time derivative of x position, so also known as the acceleration in the x direction. The sum of the forces in the y direction is the exact same equation as the x1, except the double time derivative of the position in the y direction. And the moment the moment around the z-axis, the center of mass is equal to the inertia around the center of mass times the double time derivative of angular position, also known as angular acceleration. Now, what is normal force? Normal force will always act perpendicular to the surface or plane of contact, and in our cases, it will almost always act opposite to the gravitational force, or the gravitational force times the angle of the incline the surface is on. So as you can see on the diagram on the right, where we have a box on an inclined plane. So therefore, the normal force acts perpendicular to the plane of contact on the inclined plane, as you can see in the diagram. Now for some scenarios involving friction. There are different types of bodies when dealing with friction. The first of all, like I mentioned earlier, being the maximum friction, which is the force equals the coefficient times the normal force. Then we have rolling friction, which states that the friction is always less than the coefficient of friction times normal force. Slipping friction will always invoke the maximum friction equation, like I said earlier, which is friction equals coefficient of friction times normal force. And if we have a frictionless surface, there's no friction, meaning the friction force will be zero. In these kind of problems, you will either know the friction force if the body is slipping or the kinematic constant if the body is rolling. Here's an example of a frictionless surface. As you can see in the free body diagram on the left side, there is no friction on the on on the body, meaning if you look at the equation, the sum of the equations on the right, we have the sum of the forces in the x direction equals the gravity times sine theta. As you can see, there's no friction force opposing it, so that's the only force in the x direction. In the y direction, we have the standard, the normal force minus the gravity force times cosine theta, and because there's no friction, there's no moment around the z or in the z direction because there's nothing rotating this body. And as you can see, if you solve for the x double time derivative of position, it will equal to gravity times sine theta. The normal force equals mass times gravity times cosine theta. And since friction equals zero, then we know that the angular acceleration will also equal zero because the body isn't rotating. Now, if we do with a sufficient friction body, that means that we have rolling friction. So now, as you can see in the free body diagram, we have a friction force opposing the force of gravity in the x direction, as you can see in the equation of the sum of the forces in the x direction. In the fy direction, the equations remain the same: normal force minus mass times gravity times cosine theta. And for the moment in the z direction, we have negative friction times the radius of the body equals negative value of the inertia of the body around the center of mass times the angular acceleration. Now, in this case, we cannot assume that friction equals mu times normal force because there's no slipping. Because as I mentioned earlier, in rolling friction, F should always be less than that value. You can use that value to make sure you're solving for rolling friction correctly. in that you will always get a friction force less than mu naught. If you don't, then there might be an issue in your equations or in your free body diagram. Now, this is a body that's dealing with insufficient friction, aka slipping. The free body diagram remains the same. The equations remain the same. The only difference is that now we can assume that friction will equal the friction coefficient times the normal force. Now for some applications and examples. So how is friction relevant in aerospace engineering? Friction can be interpreted as drag, in which there's friction in the same direction as airflow. This is known as skim friction. So, for example, if an aircraft is flying to my right, then we can see that friction through to the air is pointing to my left, also known as drag, also known as skim friction. Also, in aircraft takeoff and landing, there's friction between the wheels and the ground, which helps the plane either build positive momentum or try to stop it. Now for an example, a Boeing 777 with mass 200,000 kilograms is taking off on a runway with a 5-degree incline. The thrust of each engine is 400 kilonewtons and the coefficient of friction is 0.15. For simplicity's sake, we will assume the plane to be a solid cylinder of radius 30 meters. It takes 60 seconds before a Boeing 777 reaches the speed necessary for takeoff. However, the runway is only 3,000 meters long. Now we have two scenarios. The first scenario being a clear day, meaning a normal runway. The second scenario is that it's a rainy day, meaning a slippery runway. In each of these scenarios, will the plane be able to take off? Let's go over scenario one. So first, draw a free body diagram. You can see the inclined plane, the normal force, the force of gravity, friction force, and also the thrust force, which is something we haven't dealt with in the previous examples. Here, we have the given values, and then we write down our equilibrium equations, which state that in the x direction, the thrust force minus mass times gravity times sine theta minus friction equals mass times acceleration. Force in the y direction, normal force minus mass times gravity times cosine theta equals 0. And the moment in the z direction is the friction times the radius equals the moment of inertia times alpha. In this case, we can assume that alpha equals the acceleration over the body radius, and moment of inertia equals 1/2 mr squared because we assume the plane to be a cylinder. With these givens, we can assume that the friction force, plugging these values in the moment of the z-axis equations, we can deduce that friction equals mass times acceleration, which therefore we can plug that back into the sum of the forces in the x direction. And from there, we can solve for acceleration, to which we find the value to be 1.5725 meters per second squared. Now we can use the kinematic equation d equals v naught t plus 1/2 at squared. And in this case, we assume to be less than 3,000. We want the value to be less than 3,000 meters. So the plane starts at rest. There's no initial velocity. And plugging the values we were given, we can deduce that d for this, so the amount of runway required for this plane to take off, given these values, is 2830.5 meters, which is less than 3,000 meters, meaning the 777 has enough runway to take off. Now for a second scenario, the rainy day. I forgot to mention that in these in my right hand writing that the coefficient of friction equals 0.15. So once again, we have the same free body diagram as the first problem. The same sum of the force in the x, y direction equations. However, now we don't need the moment as the x equation because we can assume that because we don't need to solve for friction, we know that friction will equals the coefficient times normal force. So after solving for the normal force in the y direction, we can find the force of friction to be mu times mg cosine theta, to which we can plug that back into the sum of the forces in the x direction to once again solve for acceleration, which in this case is 1.679 meters per second squared. Now, once again, using the same kinematic equation as last time, and using the same inequality for the maximum amount of runway, which is 3,000 meters, we notice here that this 777 on a rainy day requires 3,022 meters of runway to take off, which is 22 more meters than we're allotted, meaning there's not enough runway for this plane to take off, unfortunately. That's the end of my lecture. Thank you so much for watching.